Everyone looking at class 104 here. We're doing some power and energy equations for circuits. All right, so I'm not going to go through all the math here because the math is pretty easy, but these are our power equations. Make sure you know where to find them on your reference table. Basically, power is equal to voltage times current, or current squared times resistance, or voltage squared divided by resistance. So a light bulb is connected to a 120 volt outlet. 0.05 amps flows through the light bulb. What is the power used by the light bulb? So we just use our equation P equals IV, and we get an answer of 6 watts. Okay. Next up, the resistance of a 60 watt light bulb operated at 120 volts is. So we're given the power there of 60 watts. Watch out, a lot of people think that's resistance. The voltage is 120 volts, and we are looking for resistance. So P equals V squared over R, because that's an equation that relates to those three variables. And we solve for R, and we get 240 ohms. All right, there we go. Now our energy equations are simply the power equations multiplied by time. These are also on your reference table. Make sure you know where to find them. Work is the same as energy, basically, for our purposes here. Work is the rate or is the change in energy. So if energy is being used, it's changing form. So we have work equals power times time. Work equals VI times T times time. Work equals I squared R times time, or work equals voltage squared over resistance times time. Time must be in seconds. So if it's in minutes, convert it. So working through this question here, we have 110 volts, 3.1 amps in 35 seconds. What is the power generated? How much energy is used? So you can actually find the energy without finding the power first using an equation, but we'll find the power first because that's what it says to do first. So power is equal to voltage times current, and we get 341 watts. Then we multiply that by time to get the energy, which is 11,935 joules. All right, so we got a question here. So this question here, you actually do not need to make do a whole VIRP table to answer, but it can be helpful. So calculate the resistance of a 40 watt lamp, or of the 40 watt lamp in the circuit here. So you should notice that this circuit is set up in parallel. If this is set up in parallel, what's the voltage of the 40 watt lamp? It's 120 volts. So if you want to find the resistance of that lamp, you could simply do power equals V squared over R. 40 equals 120 squared over R. And if you solve that, I think R comes out to be, let's see, I don't know that offhand. $306. All right, but let's practice using the VIRP table just for good measure, especially for your quiz. All right, so let's see. We have voltage measured in volts, current measured in amps, resistance measured in ohms, and power measured in watts. Let's throw in our givens. Oh, actually, we have our 40 watt bulb, we have our 60 watt bulb, we have our 100 watt bulb, and we have our equivalent resistance. All right, so our voltage of the battery is going to be 120 volts. Our powers are going to be 40, 60, and 100. I don't know if we can add up the power, so don't do that yet. We'll see. So this is a parallel circuit, so we know that all the voltages are the same. So that's our first step. All right, so we got that whole one. Now we have to think, okay, how can I get the current? Well, I have the power and the voltage. Can I get current? I think we just did that, didn't we? P equals V times I. So let's see. So the power is 40. V is 120. I is our unknown. Our current in this case comes out to be 1/3 or 0.33 repeating. So this is 0.33. The next one down there, you would get, let's see, I think this is 0.5. This is 0.83 repeating. And remember, this is a parallel circuit, so I can add up all my currents, 1.67. Done there. Now, how can I find R? A few different ways to do it. You can use a power equation to do it. I think that's a little bit of overkill. I would just do R equals V over I. So for example, the first one would be 120 over 1/3, repeating there. So the resistance there would be 360. That's our answer to the previous question. So notice how much more work we had to do to get there. Obviously, as you do this more and more, you could kind of do it quicker and quicker and realize that you only need to do that row. But again, for good measure, it's nice to just do the whole thing for good practice too, because this might be asking you for other things as well. This ends up being 240, V divided by I, and this one ends up being 144, I believe. Do not add up your resistors. Remember, to get your total resistance, you would have to do 1 over R equivalent. But guess what? You can just do V over I again, okay, and get 71.8. But check it out, like see if it works out. So 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. And that should work out for you. Now, how can I get my power? Well, to get this power here, there's a few different ways to do it. You'll realize you can use any power equation that's on the previous page. Use any one, try them all out. They'll all give you the same number. Or you can actually add them all up. But let's do P equals VI, which is 120 times 1.67. You'll actually find that you should get, if I'm not mistaken, 200 watts, which is the addition of all of them. There we go. All right. So the next one says a 60-watt bulb burns out, or the 60-watt bulb burns out. Fill in the chart below. What happens to the brightness of the other bulbs? So a lot of people are under the impression that they're all going to get brighter. They don't. They're actually unaffected as far as brightness goes. Why? The voltage won't change, nor will the bulb's resistance. Therefore, I equals V over R for the bulb, okay? Bulb doesn't change. Okay. Will the total current of the system change? Or the circuit change? Yes, but not for that individual bulb. What happens to the equivalent resistance of the circuit? This is something you did the last class, but you can try it out. So the equivalent resistance of the circuit will go down. What's my evidence? Well, try it out. 1 over R equivalent. Now the 60-watt one burned out, so 1 over 40 plus 1 over 100. Let's see what that comes out to be. So 1 over 40 plus 1 over 100. So in this case, you end up getting an equivalent resistance of 28.6 ohms. And the last one, what happens to the total power used by the circuit? So we already proved, okay? So this is going to be, total power by the circuit is going to go down. We already proved that V and I will not change for the other bulbs. V and I won't change for other bulbs. So what's going to happen is our power is just going to be 60 less. It's just going to be 140 watts. Okay, and there it is. Try this out in the simulation. Build a circuit, 3 bulbs in parallel, see what happens. Your values won't be the same. I don't think you can make them the same, but you can just use different numbers and just see how things change. Right? So that was class 104 for you.